to the lecture 11. In this lecture, we will continue the earlier discussed D'Alembert's principle of virtual work, and we will solve some problems involving both conservative and non-conservative forces. And then we will finally enter into a new principle called variational principle. So that's what we are going to see in the lecture. So let's rewind. What we have seen in the last lecture is we have introduced the virtual displacement concept, and by taking a dot product for the Newton's law for a particle and then summing over all particles, we found that the constraint forces, the work done, is 0, and then we finally converted this expression in generalized coordinate system such that this is a more general expression. And now if we take these generalized forces that are conservative in nature, then we can come to this equation of Lagrangian formalism, where the potential energy does not depend on q dot. So until then, you have no problem. But then we understand that a system may experience both conservative and non-conservative forces, so that the Fi can be written a combination of conservative and non-conservative forces. In this case, the generalized forces for the system can be written such that we know what is the functional form of this generalized force. So now we can write it as by substituting these conservative and non-conservative forces, which can be separately dealt by taking the generalized forces due to the conservative part and the generalized force due to non-conservative part. So the QJC basically is a generalized force corresponding to the conservative part. So you know the conservative force is a force with the property that the total virtual work done in moving a particle between 2 points is independent of the path taken. So you use, for example, if you take gravitational force, spring force, and electrostatic force. Similarly, the non-conservative forces are generally dissipative in nature. For example, friction or air resistance. And these forces take away the energy from the system as the system progresses, and the energy that you can't get back. So you may have these problems combining all. So we'll have to resolve by taking all of them into account. Thus, a system experiencing both conservative and non-conservative forces can be written in a general expression in this form. In these cases, if the generalized force corresponding to the conservative force can be derived from the potential, which is minus partial derivative of u with respect to qj. So therefore, we can replace this term by this part. So in that case, your equation will come out to be, so qjc is replaced by the potential derivative. And now if we assume that the u is independent of the velocity part component, then we can bring this term on the left side, taking the partial derivative of potential with respect to q dot as 0. Now this is nothing but L. So therefore, in such case, we can write this equation in generally as a Lagrangian formalism, where the Qj Nc on the right side is due to the non-conservative forces. This is no doubt. So now taking these examples, taking this idea into picture, let us work out problems with the virtual work and generalized forces, how we can adopt these non-conservative forces in the problem solving. And this problem we have already solved in the last class, therefore I am not going to explain it, but I will come else explain that the solving problem is not only in a way, you have multiple ways to solve, and just we'll see one of the way. So we have solved by taking the virtual work concept such that the total virtual work done on a static system by the external forces vanishes at equilibrium. So this is what we have taken out. Now, and then we find out all this, finally we derive this formula. So can you choose, we can choose any other variable to solve the same problem so that we can get it. So let's see what is the constraint quantity here. The constraint quantity here is the x square plus y square is equal to L square all the time. That you can understand very easily. So now by taking that into account, if you can exchange this coordinate such as y equal to root of L square minus x square. Now if you take a partial derivative of y, or not partial derivative, if you take a derivative of y for delta y, so then you have, for with respect to delta x, L is a constant, so therefore this function turns out to be here. Now we have delta y and we can adopt it in this equation. So the total virtual work done in this process, we can write it as here. Now you substitute delta y here, so we end up in this functional form. So take out the delta x commonly, so you have f minus mg x by L square, x square under root. So now we can write it in this form. Now what mg is known, what is this x under root square? So we can take x here, and then this side will be y equal to L square minus x square under root. So therefore this is nothing but tan theta. So x by L square minus x square under root will be simply tan theta. So you can also solve by this method also without any difficulties. So choice is with you in solving the problem. Let us continue the another problem where we have solved already this problem in tutorial number 4. The problem number 4 is explained here. You have a spring pendulum where the mass m is attached to a spring which can expand with the time, and then we have done the Lagrangian equation for this system. And now the same system, now we are going to extend by a non-conservative force that is acting upon a mass along this particular direction. In this case, how the Lagrange's equation of motion gets modified. Let's look at it. Now in order to solve it, we'll have to separate conservative and non-conservative forces. So the conservative forces here are the mg acting downside, and the restoring force, the spring that is coming from this with the corresponding potential, and the non-conservative force is here only the f of t. So let's see how to go ahead with this problem, and then we can say. So we go as usual like what we did earlier. So first find out the degrees of freedom and choose the generalized coordinate. So since this is in xy plane, obviously the z is 0 and there is only one mass, so therefore it should have 1 into 3 degrees of freedom totally, and because the z is constrained, so you have only 2 degrees of freedom here, and these 2 degree freedoms are, one is theta, the other one is this expansion of the, like when the length of the pendulum which varies with the expansion, so that is s, we can take it. Once you have this standard generalized coordinates, now the next idea is to find out the transformation relation. So the transformation relation, so the x will be L0 plus s sin theta, and the y will be s plus L0 into cos theta. So that is also there. Once you have that transformation relation, write both t and u in Cartesian. So you have kinetic energy term and potential energy terms. And now you convert this in the generalized coordinates. So we can substitute for x dot from here and y dot from here, and then your kinetic energy, potential energy now comes in the form of generalized coordinates. So this you have done it, therefore I am going little faster. So you get finally the Lagrangian in this functional form. I hope there is no difficulty here. Now, how are we going to adopt the generalized force corresponding to the non-conservative force? So how are we going to do it? So now we need to write the generalized form of it, which it is given as the non-conservative force Qj is F dot the partial derivative of R by generalized coordinate. Now, if I look at it generalized coordinate here, I have two generalized coordinate. One is S, the other one is theta. Therefore, we should have two generalized forces corresponding to each coordinate. That's what you have to careful. So you supposed to get equation of motion for each coordinate, and therefore there should be a corresponding generalized forces for non-conservative force for each part of it. So here the force is acting along only x direction. So therefore, can I say that we can write it as the two generalized forces corresponding to two generalized coordinate as, now we are going to split it. One is as a QS, so non-conservative force. The other one is Q theta, non-conservative force. And we know what is F. F is along x direction. So we need to know what is R. R is a position vector which can be written as x cap plus y cap. So you know x from earlier and y. So you put it so that you get a R cap. Now what we have to find for first, let us resolve this part. So we need the partial derivative of R with respect to S. So if you do R with respect to S, you will have x cap sin theta plus y cap cos theta. So that is what you will get it. The partial derivative of R with respect to S is here. Now you put this one equation here so that we can get the Q generalized force for the generalized coordinate S as F dot the partial derivative R with respect to S. So now you know this is Fx dot x sin theta plus y cap cos theta. So since x cap is 1, so you'll have F sin theta component adding to this generalized force for the generalized coordinate S. Similarly, we can do it for here in this part. So we take the derivative of R with respect to theta partially, then in this case you will have x cap s plus L naught cos theta, that will be minus, sorry, this is plus sin theta, here y cap s plus L naught minus sin theta would be. So the partial derivative of R with respect to theta comes out to be this part. So let us substitute it for this part so that the generalized force for the coordinate theta, generalized coordinate theta is like this. So now substituting fx here, this term, so you have f s plus L naught cos theta. So now we have the generalized force corresponding to each generalized coordinate. Now we can go on putting it in the general equation so that we can get Lagrangian equation for each generalized coordinate. So let us write, this is a generalized way of writing it. So this is your Lagrangian that we got it. Now let's do it for each one, S and theta separately. So therefore if we write this equation for S, so the q dot j I or j whatever is that, this will be j. So then this will be for s dot, this is for s. So you have this side. So now if you take a derivative of L with respect to s dot, you have only this component. So it will be ms dot. Similarly, derivative of L with respect to s. So you have here and you have here. So all terms would come out and s also here. So m s dot d by dt is here. This is the first term. Whereas the partial L with respect to s, you have term corresponding to here and this term and the spring force, this also coming, that is equal to qsnc is f sin theta. So you have now equation. Now if you put it in the proper form by taking a time derivative, so it is ms double dot minus all these terms, you can rearrange it. This is the final form of equation of motion having non-conservative forces for this particular generalized coordinate S. Similarly, we can do it for theta. So theta dot theta, so we can do it. So if you do it with the theta dot, then this term will come now. So we can d by dt of m s plus L naught square theta dot is here. So the remaining term here, theta is, it will become minus sine theta, and this side is fs plus L naught cos theta is there. So taking that, we will have the final form of equation now, which is in this functional form, having on the right side the term related to the non-conservative forces also coming. So this is how you have to solve it. But then we are very good in solving some of these friction related problems. So let's look at that way, then we can understand it very easily. So here we have a problem where a block of mass m is sliding down the plane as shown in the figure. The frictional force is acting on the particle in the opposite direction, for which you obtain the Lagrange's equation of motion. Here the frictional force is non-conservative because it is a dissipative in nature, and see how to do it. So if you carefully look at it, if alpha is 0, the mass m would be simply sitting down here, right? Somewhere like this, for which you will have a mg acting down and then normal force acting upward. So there is no friction here. But then as and when alpha is increases slowly until a critical value, now the mass will start sliding down with certain speeding up acceleration. So therefore, when alpha increases, then this mass starts sliding, giving acceleration, and then the friction also accordingly plays. So there should be finally a functional form relating acceleration, friction, and this angle when you solve the Lagrange's equation of motion, right? Let's see how to put it up. So since this is a in a plane, obviously you have to start looking at the generalized coordinates. So and then you have to use this Lagrange's equation including these generalized forces, where we have to resolve these uh, non-conservative forces. So let's go the same way step by step. So find the degrees of freedom. So the degrees of freedom here is one z is 0, so 1 is out, and then y and x are correlated through this angle alpha. So you have two constraints in this problem that gives the degrees of freedom to this problem as only 1. If only 1, that can be represented by s. So once you know the degrees of freedom, find out the transformation relation. So you have x, which is s cos alpha, and y, which is s sin alpha. And then you put this in a Cartesian, t and u in a Cartesian frame, so which is half mx dot square plus y dot square, potential energy is mgy. Now you put this, now you can change this one in the generalized coordinate format. So you know x here, x dot you can get, y dot you can get, and your t and u now in generalized form comes out, for which the Lagrangian can be written as very simply L equal to t minus u. So this we got it. I think here up to this you don't have any difficulties, but now we have to go on placing this non-conservative force. Now which side the force is acting upon? So let's go back. So the frictional force is acting along the s directions here. So therefore, the sixth step that you have to do it, find the generalized force corresponding to this non-conservative force. So you can write it. Here you have only one generalized coordinate, which is s. So therefore, the q can be written only for the s part of s generalized coordinate, and only one non-conservative force, that is f only, that is acting along s direction. So s cap. So therefore, now we can write f, that is nothing but f s cap. So that can be resolved as x direction as well as y direction. So x direction will have x cap the x cap cos alpha, and y cap sin alpha for the y direction. So similarly r vector is x cap, y cap. So you know x and y, you got the relations. So here also no difficulties in solving it. Now we need to find this term. So now we know R, so we can take the partial derivative of R with respect to S so easily, and you have F. So let's put together and see what turns out to be. So if you do that, so the partial derivative of R with respect to S is S cancel out, x cap cos alpha, y cap sin alpha comes here, and now let's bring it F. We know the partial derivative of R with S, so you put it together. So here x, this is x, so cos square alpha, and this is y cap sin square alpha. So cos square alpha plus sin square alpha will eventually turn out to be 1, and therefore you have only F coming out. Now if we write knowing L and knowing Q, now we can write the Lagrangian equation for this generalized coordinate such that it turns out to be here. So we can write it as for the S only. So this is S dot S, here is a QS. So we know now this taking a partial derivative with respect to S dot will be MS dot, and similarly with respect to S will be mg sin alpha. So we can substitute it and you will get, so again taking a time derivative will give ms double dot plus mg sin alpha is equal to F. Or you can rewrite it such that to get a meaningful explanation. So what is here, when I increase the alpha value slowly from 0, the sin alpha gets increased. If sin alpha gets increased, the frictional force has to balance it, for which the acceleration slowly happens such that the mass start moving towards downside. That depends on the sign. If this term dominates, S will be down the angle, giving acceleration towards the downside. So you have that physical correlation bringing the equation of motion. Okay, let's extend the same thing problem based on circular case, like circular motion. So here you have the same mass, similar mass rotating in a circular orbit along the inner surface of the ring. Now the frictional force is acting on the particle in the opposite direction of its instantaneous velocity. Obtain the Lagrange's equation of motion for this system. So now you have to be careful. We always remember that when you represent r and theta cap, so we write the r cap in this direction and theta cap in this direction. But now theta cap goes towards my left side, towards this picture. But now your frictional force is acting on the right side. So the frictional force is acting along the minus theta cap direction. So that you need to catch it up. Okay, now let's go by the same way we will follow it. Since this is the xy plane, you have one constraint as z is 0, and now these x and y are related with the r. Therefore, x square plus y square is equal to r square. So you have two simple constraints. So therefore, we can get the degrees of freedom as two constraints, leaving for a single mass with 3 degrees of freedom now will be reduced to simply 1, which can be simply theta. So theta is good enough to explain this problem. Now once you have this degrees of freedom, so you can find the transformation relation. So you have x, which is r cos theta, and y equal to r sin theta. And once you have that part, now you go on writing it t and u in Cartesian. So you can very well say that without any difficulties. And now you go back and have it with the generalized format. So we know x, so x dot square find y dot square and put it up so that you can come back with all the explanation. So the t and u in generalized format will turn out to be for which the Lagrangian can be written in this functional format. There's no issue with that. Now we have to find the generalized force corresponding to the non-conservative force. So here again only one generalized coordinate. So therefore you'll have only one qj. Q is simply 1. So that would be basically you can write q theta which is f dot partial derivative of r vector with respect to theta, because one generalized coordinate and non-conservative force. Now we have to resolve what is the direction of this f. So f can be written here as, because as we said, this is acting along minus theta cap direction. So therefore we can sort it out. F as f in acting on minus theta cap, you know how to write theta cap earlier in polar coordinates. So that is x cap sine theta minus y cap cos theta. R is known, so therefore we get r part also. So from here we can get the partial derivative of r with respect to theta. So what would be? So we can say the partial derivative of r with respect to theta is minus r sin theta x cap and plus r cos theta y cap. So now we have all the terms f, partial derivative of r with theta, find out what is q theta non-conservative. So which will be here f, so this will be minus r sine square theta minus r cos square theta. So taking minus r outside, it will be sine square theta plus cos square theta, leaving minus fr. So we can rewrite then the Lagrange's equation of motion for the generalized coordinate. We have only theta here, so the equation turns out to be this way. So L is known, so we can find out what is this term and put it up all together. That will give us mr square theta dot minus mgr cos theta with the minus sign equal to minus fr, or we can write it this way. So this also again can explain the equation of motion of the system beautifully, the same as the previous way. So basically we can adopt all such non-conservative and conservative forces carefully in the Lagrange's equation, and then you can find out equation of motion depending on the type of forces involved in the system. I hope with these problems, the problem you solve in tutorial, you have now ways to adapt for solving the problem. Okay. Now let's go into the new concept, which is the variational principle. This principle can be used to solve the problem called Barchistochrone. The Barchisto means shortest and the crone is time. So this is the way of finding the shortest time for certain process. Now, if you look at in science, particularly in mathematics, the variational principle is a method that enables a problem to be solved using calculus of variations, which basically talks about finding functions that optimize the values of quantities that depend on those functions. Something not clear, right? Don't worry. So I'll give it very easy way of it. Or otherwise, if you say it, the calculus of variations is a kind of branch of mathematics which considers extremal problems, maxima or minima are stationary. It basically yields the techniques for determining when a given integral, definite integral, will be maximum or minimum or so on. Is it clear still? No. Okay, let's take a simple example. What is the meaning of it? If I consider a plane, so let's draw a simple plane to assume it. I have a simple plane and I consider two positions A and B. Now, what is the shortest length that would be connecting between these 2 points on a plane where there are no constraints? And obviously, you without hesitation, you are going to tell me, sir, it is a simply straight line. Is it straight line? Let me write. So it is a straight line. No doubt about it. Very well understood. Still, We will solve a problem to derive the straight line is a straight line in the next class. Now, if I consider the same point A and B in a different situation, for example, let me take a surface and I put a straight wire, a straight pole. Let's assume that there are two poles with the equal length. Let's say L. Now my point is A here and the point is B here. Same as the way I connected here. Now, would the shortest path between these 2 points be straight line or something else? Now, what is the constraint here? Are there any constraint here compared to what we seen on the problem 1 compared to this? Are there any constraints? Yes, there are constraints because you kept a vertical pole and therefore the gravitational energy has to do something with that. So in such case, a gravitational force will try to do something so that something will happen. So in this case, it's like, we use a rope for hanging the cloths for drying it out. So you have 2 points connected on the wall or on the standing one, and when you tie it, would it be straight unless it is a constraint? So that is what will happen. So now if we have something under constraint, what would be the shape of it? Would it go or will it go like this? Sorry, would it go this way? Okay, assume that. So these kind of solving a problem on the surface, how this curve nature varies under constraints is called to be geodesics. Geodesics. This is called problem solving geodesics. So that talks about a mechanics, that's a principle of least action or stationary action. Now, if this is getting a different ideas, now what will happen if I take another surface? Suppose I take a sphere. I want to find out what is the shortest between the point A here and the point B here. Would it be a straight line? Just connecting the points between these two. And if I go for another system, for example, cylinder, let me take a point A here and a point B here. Can I just connect it by a straight line dot between them? Or I take another surface which is a cone. Now what happens to my two different points? One is A here and another point on B here. Would it be simply straight line? So when you want to talk about all these different type of situations, we have to deal with this variational principle which talks about the stationary action principle when applied to the action of a mechanical system, which will eventually yield equation of motion for that systems. Or the principle states that the trajectory that you are talking about are stationary points of systems action functional. So obviously we put the question, what is the path that gives the shortest distance between 2 points in a plane? We said it to be straight line without any hesitation, but can we say here as a straight line? What is the path that gives the shortest distance between 2 points on a sphere? Would it be a straight line, or what would happen for the in a cylinder and so on? So when these comes, so you have to use this concept called variational principle. It's not new. You would have heard about it when I come to next slide. Then that's nothing new. So it's all same thing. But then we are using a new technical term called variational principle, and therefore you are getting a little bit confused, but nothing to worry about it. Now, to deal these concepts, there are so many legends involved here. Although it is said to start with the Newton's minimal resistance problem somewhere in this 1687, the shortest time problem was raised by the Johannes Bernoulli. So he raised the problem, the shortest Barchistochrone problem in 1696. But before that, altogether, the Fermat said, we call this Fermat principle, that when a light follows a path of shortest optical length connecting two points, the optical length depends on the material of the medium. So that's what Fermat says as a Fermat's principle, called principle of least time. We will see in the next slide. So like this, a lot of deliberation happens parallelly, but then later Euler brought a geometrical explanation for this system in somewhere 1733 or so, but then he stopped his work because he found that the Lagrange's work in his age of 19 years old, like you all, that he saw it's his approach is very nice. The analytical approach by Lagrange is very much impressive, and Euler stopped his work and started appreciating the approach by the Lagranges, and that is how this calculus of variations and Lagrange became a dominant process, a mechanism to deal with a lot of mechanics. Okay, let's see where and how to understand it, because talking history is okay, and then we need to understand the physics behind it. Now what you see here is a kind of a container in which a salt solution is placed with refractive index varying from top to bottom. So at top the refractive index 1.33 and bottom it is more than 1.33, so that there is a gradient of the refractive index. Now let me take a laser light and just point it out towards this solution. So the light supposed to pass through this medium without any difficulties, fine, and at the end of it, it is going to come out. Now the question is going to happen, what is the path it is going to happening inside this solution? Before doing so, let's see what happens, the Fermat's principle explanation, where you consider a medium with refractive index N1, there is another medium with the refractive index N2. If a light travels from a point A to point B in the medium 2, then we explained it by using this Snell's law. So you have connect. Oh, this is because of pen movement. So let me put it. So let's connect this point and connect this point. So this is theta 1 and this is theta 2. This is very well. So the light travels in this path to reach the point such that the sine theta 1 by sine theta 2 is given as n2 by n1. No doubt about it. Now you ask yourself question, or at least I have question, that how this light travel a shortest path to reach from A to B. How do I confirm it? Why it did not take, let's assume this is path 1, why it did not take this path to reach here? So let's say this is path 2, or it did not go by this way. This is path 3, right? So it could have gone in any of these possible paths, but then we believe that it has taken a path 1 to reach from A to B. So if that is the case, we need to show or prove something such that it is the truth. So in the same way, if we understand this in the container, will the laser rays simply pass from the starting point of this solution, this left side to right side, just in a straight line? Or would it go in the curved form showing this way? Or will it be taking this path? We do not know, but we only know that the light is going to travel a path which takes a shortest time between them, right? So if that's case, then we are going to say that the light, which we all know which path is going to do that. So the Fermat principle says that the light traveling between 2 points along the path that requires the least time compared to the nearby path, any other path you consider. So for example, it's going to take 1 instead of 2 and 3. So in that case, we can write the travels in a path for which the time has to be minimal. The delta t is as small as possible, least time. So which can be written as the functional form delta of the path moving from A to B should be reaching in a shortest time. Now, the shortest time can be expressed provided you know the infinite smallest path or elementary length that you have ds here, and if it is traveling in a particular speed, that should be tending towards 0. So we need a condition for finding the minima of this integral. So how do we do that? And that's what we are going to talk about in next lecture, that how the Lagrangian formalism is going to come into picture in saying this condition for minima of an integral. Okay, now we often see the stone's trajectory. We throw from one side to the other side. It has a particular path or trajectory. And we also know that in the theme parts, the roller coasters are there. So you can see that the design of the roller coaster has this functional form. But we never ask ourselves, why is it so? And now, if I have to consider a point anywhere in this roller coaster between A and B, is going to give me something. That's why the design of such things are very, in this particular format. So if I say so, then what we are going to say, let us consider a point 1 and 2 in a plane xy. Now, how to reach from the point 1 and 2? Would it be some curvature form, or would it be a straight line, or would it be some other form of it? But all eventually has to give certain things called shortest possible time, or Barchistochrone. That's what we have to finally conclude it. So how do we conclude it? Let us take a mathematical way of showing it. So for example, this is the one simple demo that is given in Wikipedia. So I have 3 different construction of path to reach from point A to point B. So one is just a straight line, the other one is a L shape, the third one is a curve. Now, which of them reaches fast? So if I release all time 3 particles together, so what is showing your curve? The red one gives the fastest reaching for some reasons. Is that true? And if it is, how do we prove it? So we'll have to show it such that yes, it is true. Okay, so how do we approach it? So let's take a simple path connecting between 2 points A and B like this. So let us take a elemental length ds. So that can be resolved by component x and component y. So therefore, we can write ds as dx square plus dy square under root. So either I can take out dx outside or dy outside, such that this equation can change into another functional form, 1 plus dy by dx square, dx going outside. So if I can write this as a y prime, so my equation will go into 1 plus y prime square under root dx. Now what we are saying, the time that takes from A to B should be minimal through this integral path such that the I, which can be the integral path, is we can write it from A to B nothing but ds by V. So what is ds? So we know ds here. What is V here? It is the velocity. So that can be find by what is this point? We can take all the energy as a potential energy. When it comes here, it will be converted into kinetic energy. So by using the rule of conversion of energy or conservation of energy, so we can write mgy as a half mv square, where we can take v as a root tgy. So whole function that you have inside can be written as some functional form. Carefully look at it. It looks something similar to what we follow Lagrangian Q, Q dot and T. Correct? Okay, fine. If that is true, then what we need to find is something outcome of it. For example, this is a cycloid. This is a cycloid that you see the animation here, which can be represented by taking a circle with the point moving on the straight line. You see here, the point is fixed on a circle which is allowed to move on a straight line, will give you a form of path called cycloid. And this cycloid can be explained in this functional form. We will see that soon in the next lecture about the properties of it. So what it's saying, so if you consider a function which has y, y prime and x. So let us recall it similar to L, Q, Q dot T, where the y is itself a function of x. So therefore, y prime would be simply the derivative of y with respect to x, such that the function f is a function of function, because y is also a function of x. So the f is function of function known as functional. So all we need to is that find out this integral condition to get a shortest time, so that we can do it. So let's take a simple example. For example, if you have to do that, you need to know the integral path y of x in order to do so. So if I take a simple example, f as some functional form xy and x square y prime, and now this function y is again a function of x square that is shown here, then the function will, the capital F will be turned out to be x square, it goes here, and y prime is dy by dx, so therefore this is x square 2x. So totally giving 3x cube. And if this has to be a shortest one, then the integral that you get it from x1 to x2, moving from this point to this point, x1 to x2, for this function, giving this result should be as smallest possible, or we say call it as a minimal, to give a stationary condition. Hold on, we have not completed it. We will give more physical explanation in the next class. So due to time limitation, we are stopping here. So if you have any questions on this, we can continue and clarify. We will continue the discussion on this particular concept more later.